Good afternoon, folks, and welcome back to a little kitchen chemistry lesson. Today we're going to be talking about the pH scale. And you've heard the term pH scale before because it gets used a lot. We hear it when we're talking about the concentration of things in a pool or a bathtub, when you're making the right pH levels, when you are mixing certain types of paints in art class, when you are creating different types of foods and chemicals. We talk about pH. pH refers to the concentration of an acid, how acidic or how basic something is. Way down here at the bottom end of the pH scale is our super acidic stuff, really, really strong acids. And at the top of the scale, 0 to 14, so the 14s, we have really, really strong bases. Anything up of 7 is considered a base. Anything below 7 is considered an acid. And we know from our lesson yesterday that an acid is something that releases H plus ions. And a base is something that releases OH minus ions. So they're kind of in a balance, because what happens when we combine H and OH, we get H2O, water, pure water, 7. So if we're combining H's and OH's, this is a hydroxide ion and a hydronium ion. When we combine those things and we're making water, we have acids and bases in kind of a balance. And if we mix them in perfect quantities, we will end up with salt and water, this pure, harmless substance, where either a base or either acid can be very, very harmful. So what do these right here, what do these numbers actually mean? Well, those numbers on the pH scale actually refer to exponents. So if we have a substance with a pH of 1, that's a very strong acid, way down on the pH scale. That actually means that it has a concentration of 10 to the negative first molar, 10 to the negative 1 molar. So break that down a little more, 10 to the negative 1 moles of H plus ions, moles of hydronium per liter. That's about 0.1 moles of hydronium per liter. That doesn't necessarily seem like a lot, but H plus ions are incredibly reactive, and when we have a high concentration of them like this, they can be really, really damaging. And it's really, really harmful. So let's look at something that has a pH of 2. So now we've moved up the pH scale, so we're actually getting less acidic and we're getting more basic, closer to neutral. So if we have a pH of 2, that's 10 to the negative 2, 10 to the negative 2 moles of H plus ions per liter, and 0.01 moles. So you can see here we moved the decimal point over 1. So the pH scale is really more like the Richter scale. It's not a linear graph. So as you get lower on the scale here, you get exponentially more acidic. And when you get higher on the scale, you get exponentially more basic. So 6, 7, 8 don't really vary very much. But when you get farther out, you start to get exponential growth. So here's the reading for today that you're going to be doing. If we look at this graph right here, this chart, this is a really, really complex chart. And I wanted to draw this to your attention because I know your eyes are going to roll into the back of your heads when you see it. But let's just break it down real quick, okay? So down the middle, we have the pH scale from 0 to 14. And right here are H pluses. So with a pH of 0, that means that we have 1 mole per liter of acid. That's an incredibly high concentration. If we have a pH of 0, that means we have 10 to the 14th OH minus ions. These guys are always in a balance, okay? As we go up the pH scale, we're increasing H pluses and decreasing OH minuses. As we go up the pH scale this way, we are decreasing H plus ion concentration and we are increasing OH minus concentration. The only point where we have the exact same number of H pluses and OH minuses, 10 to the negative 7th, 10 to the negative 7th, is right at a pH of 7, pure water. So when they exist in a balance, they're neutral. When we have a increase in one or the other, hydroxide or hydronium, we get a base or an acid. So I'm going to let you guys read about this, but I wanted to show you just some stuff that you can play around with the acids and bases in your own house. Everything that I'm using today is going to be a very dilute acid. We're not going into these ranges out here. If I was going deep into these ranges on either side of the spectrum, I would be wearing gloves, I would be wearing full sleeves, I would be wearing closed-toed shoes, I'd be wearing goggles. We would not be messing around. But we're staying pretty close to the middle here. We're not going to go higher than 3 and I don't even actually have real bleach. I have Drano, which is still caustic. You don't want it on your skin, but it's not full-on bleach. It's more over here. So I've talked to a couple of you guys about this, kind of giving you a heads up, but not everybody. What we are going to do today is we are going to mess around with cabbage juice. So what I did was I got a cabbage from the grocery store. Whoops. I chopped it up and I boiled it in water. And you get this really nice, pretty purple color. Cabbage juice smells terrible, but it looks delicious. All right, so I have a bunch of these glasses that are purple, okay? Really cool thing about cabbage juice is that it is a universal indicator. An indicator is something that, it indicates it tells you the pH of a solution. Most indicators are only precise under a very short range. Lab indicators like phenolphthalein or methyl orange, which unfortunately we don't have the opportunity to play with in virtual learning, will indicate a very specific pH range. Is this between 3.5 and 4? Is this between 7 and 9? But they don't go, these indicators only indicate a small range. So like phenolphthalein is red in an acid, but anything below a 5, it's basically, my numbers might be a little off, I'm doing this from memory, but it's just yellow or it's red. And it's pink in this kind of middle region. But so it's got an indication of a very small area. Cabbage juice is dope because cabbage juice will indicate and change color in a big rainbow all the way from like way down in acids all the way up to bases. So let's just mess around with some like things you might have lying around your house and see if they are in fact acids or bases. Let's start with something that like we know for sure, right? Let's start with lemon juice. We talk about lemon juice being like a very acidic. Fruits, these are citric fruits, refers to citric acid. So what happens if we take lemon juice and we put it into cabbage juice? Look at that. Turns that really pretty nice red color. If we had stronger acids, we could turn this like bright, bright pink red. But don't mess around with those because that's unsafe. So in this, using this indicator, let's put acids over here and let's put bases over here. So first we have lemon juice. Lemon juice is an acid. Okay, so now let's try baking soda. You only need a little bit because baking soda does not dissolve super well in water. It's just a little bit. Oop. Look at that. Nice, kind of soft blue color. So, baking soda is a base. We use it a lot in cleaning products and things like that. So I'll put this up here. Baking soda. All right, and let's do another one. How about vinegar? This is rice vinegar. Any kind of vinegar works fine. The main ingredient in vinegar is acetic acid. A little bit of vinegar. Look at that. So you'll see, here's my lemon juice, here's my vinegar. They're a little bit different. They're not exactly the same. So let's see here. Part of the reason they're not exactly the same is because lemon juice is going to have pulp in it and little bits of particulate matter that kind of disperse light. So the vinegar is going to look much clearer and crisper, and the lemon juice is going to look a little more cloudy. But also, rice vinegar is not quite as acidic. So this lemon juice is more like a kind of a darker or more of a brighter red, where this guy is a little more magenta. It's a little closer to that purple color in the middle. So our second one was rice. I'm not going to spell this one wrong. Rice vinegar. All right, let's do another one. Why not? Let's go for the Drano. Why not? I haven't actually done this one yet, so this will be new. Actually, you know what? I'm gonna get gloves on. I'm gonna be responsible. And we're back. Drano is meant to dissolve organic matter in your drains, so you're gonna probably want gloves on if you're messing around with bleach or Drano or something like that. So I am going to use a little dish here. I'm just going to put a little bit of Drano in there. Let's see what it does. This is an example of kinetic molecular theory. Neither of these liquids are moving very quickly, so the reaction is proceeding very slowly. If I give it a stir, whoop, there it goes. Real quick change. Add a little more, why not? All right, that's cool. So now let's compare baking soda, nice little blue, to Drano. That got really dark green. So when you put cabbage juice in a base, it goes from that purple toward more of a blue, and then eventually out to a green and like a really deep yellow when you get out there with bleach. So we have Drano. Now I got a couple more things here that we can mess with. The last one I have is an air freshener. So let's see what this does. Little technical glitch, and we're back. So we were just messing with this air freshener. It went into this glass. Nothing happened. So what does that tell us? That tells us that this is not an acid or a base. This is neutral. And it goes right there. Does something being an acid or a base, not being an acid or base, being neutral, does that mean that it's not reactive? No, that is absolutely not what it means. It just means that it is not an acid or a base. Lots of things can be reactive. To demonstrate that, get rid of that. Let's get a new serving of cabbage juice. There we go. So, purple, okay? Now, I'm going to put a little nail polish remover in there. Okay. Cool. Nail polish remover. Did that change very much? No. It got a little more red maybe, so maybe nail polish remover is a little bit acidic, but it's still pretty purple. So even though nail polish remover is not really acidic, it's still a pretty powerful chemical. And I have a way of showing that. So I removed the cabbage juice, so now we have just the nail polish remover in there. So let's see what happens, even though with this relatively neutral substance, we introduce a little bit of energy. Always make sure that you have something on hand to put out your fire if it gets a little unruly. Look at that. Isn't that cool? So this is not to put the fire out. This is just a little experiment to show you. Oh, there it goes. We're getting so deep in this video. The water is denser than the acetic acid, so they don't mix, and the water slides under it, and the acetic acid floats up, and those fumes continue to burn. So a substance that is not acidic, that is not basic, that is pretty neutral, can still be very, very reactive. So don't try that at home. That's just a little demo. You don't want to mess with that. This is a tempered glass right here. This is like strong glass. Most glasses, if you did that, would shatter. So keep that in mind. Don't mess around with that. All right, guys. So in summary, your acids will release H plus ions. Your bases will release OH minus ions. The more ions they release, the more acidic they are in either direction. And where they meet in the middle with a perfect balance of OHs and H pluses, you have neutral water. So let's try one more thing. Baking soda is a base. Vinegar is an acid. What happens if you make baking soda and vinegar together? Look at that. Back to purple. It's a little darker there, but we're back to purple. I can go the other way. I can go back the other way. There we go. Nice purple there. So these things exist in a balance going back and forth between OH minuses, bases, and H pluses, acids, and in this constant balance or equilibrium of concentrations.